Section 6.3, inelastic versus elastic collisions. The objectives here are to differentiate between an elastic collision and an inelastic collision, and to determine and calculate the relationship between the conservation of energy and the type of collision. First, an elastic collision is when two objects collide but maintain their shape and move independently after the collision. And in these scenarios, the energy is conserved. Now, we've seen this already in 6.2, and this equation that results is m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. So again, the objects are separate beforehand and they're separate afterward. With a perfectly inelastic collision, we have two objects colliding, but they deform. And then they move together as one mass. They fuse together some sort of way. And after the collision, the kinetic energy of the system decreases. And why does the kinetic energy of the system decrease? Because some of the energy in the system is used to make these two objects fuse together. So this equation would look like the following. m1 v1i plus m2 v2i, but now they fuse together and they're one mass afterward. Quantity m1 plus m2, and since they're moving together, they have the same velocity afterward, so it's simply just vf. Now something good to take a note of is that most collisions are somewhere between elastic and perfectly inelastic. We simply just call them inelastic collisions. Okay, the reason being is that elastic collisions here are collisions where the energy is conserved. But a lot of the time we have elastic collisions where the two objects move independently afterward, but the energy of the system is not really conserved. And you have to think logically. Even if two hockey pucks hit each other and they bounce off and you say that the energy is conserved because it's elastic, really the interaction between those two molecules or those two bodies and the molecules on a subatomic level give off some energy, whether it's vibrations when they collide, or if the two objects collide and make some sort of a sound, there's some sound energy. So kinetic energy in the system is really never conserved when there's some sort of a collision involved. So we really say that equations are not really perfectly inelastic, but they're neither elastic, it's somewhere in between here. So a lot of the time they hit together, these two hit together, but then they move apart separately, but the kinetic energy is traditionally not conserved. We're going to be dealing with problems in this section that are just elastic or perfectly inelastic. Example 1 says, an empty train car with a mass of 1,500 kilograms is moving east with a velocity of 25 meters per second, and it collides with a loaded train car with a mass of 2,500 kilograms that's initially at rest. If the two cars stick together, determine the velocity of the two train cars after the collision, and then determine the loss in kinetic energy due to the fusion and deformation of the train cars. So we have two train cars. This one's about to collide into this one. Well, this one's initially at rest. This one is moving initially with a velocity of 25 meters per second. The mass is 1,500 kilograms. This mass is 2,500 kilograms. Now, after they collide, they're stuck together. So they're moving as one now, as one body forward. And we are trying to figure out, A, what is the velocity of them afterward, and B, how much energy did it take for these two cars to stick together? Now, so let's go ahead and find part A first. And we'll notice that this example is inelastic in nature because they're sticking together. So let's go and think about our inelastic setup right away. So inelastic, beforehand, we have the first object moving, but the second object is not moving initially, so we can put a 0 for it. But then afterward, we have them stuck together, and they're moving as one. And we're trying to find VF, so I don't have to even think about this part of the equation. I can just divide by the quantity m1 plus m2. And that drops this off. So VF is m1 v1i over m1 plus m2. Let's plug in our numbers. We've got 1,500 times 25 over the sum of 1,500 and 2,500. That gives me a final velocity in this problem of 9.4 meters per second. Now, what do you notice right away? The answer clearly makes sense because my velocity had to go down. The velocity initially of the one car was 25 meters per second, but once these two cars are joined and moving together, it's got to have a lower velocity. So now the velocity is 9.4 meters per second. Let's figure out how much kinetic energy was lost in this process. So we'll find our kinetic energy initially and kinetic energy final. Initially, only the one car is moving. There's no second car movement, so we don't have to worry about it. And at the end, both cars are moving, but they're moving together. And we know all these values. If I plug in for these numbers here, we'll have 1/2 times 1500 times 25 squared, giving us 468, and I'll round to the nearest 10th, kilojoules. That's 468,000 joules. And the kinetic energy at the end, when plugging in here, we'll have 1/2 times 4,000 times 9.4 squared is 176.7 kilojoules. So what's the difference in those energies? Delta KE is equal to KE final minus KE initial. And subtracting those two quantities, we're going to get negative 292.1 kilojoules. This is the amount of energy lost due to friction. Okay, the friction that causes these two objects to fuse together and to form. So the energy needed would be 292.1 kilojoules in order for this to occur. Also note that this is just like our Q loss. Example 2 says two objects collide elastically and head-on. So right away, elastic collisions. The first has a mass of 15 kilograms and a velocity of 3.5 east. And the second has a mass of 25 kilograms and with a velocity of 4 meters per second, but it's west. So we see the opposite signs in our velocities. Next, we want to know, or we find the final velocity of the 15 kilogram object being negative 5.875 meters per second, because again this is west for this one now, so it rebounds. And we want to find the final velocity of the other object. Now, right away you should suppose that the other object will most likely be a positive answer, because it looks like these two objects are colliding and they're rebounding in the opposite direction. We're going to then verify our answer by calculating the total kinetic energy before and after the collision to see that they are indeed the same and that energy is conserved. So in this problem, we can go ahead and solve this original equation algebraically for V2F. All we're going to do is move this over by subtracting and then divide by M2. So our generic solution will look like the following. M1 V1I plus M2 V2I minus M1 V1F all over M2. And if we plug in all the numbers from above, we'll see that we'll get a value for V2F of 1.625 meters per second. Now we want to verify that this is correct by looking at the kinetic energy before and after. The kinetic energy initially is going to be 1/2 times the first mass times the first mass's velocity squared plus 1/2 times the second mass times the second mass's initial velocity squared. The energy after is going to be the same thing, but with a final instead. We know all these quantities. What we'll end up getting for each of these is around 291 joules. To be exact, it's 291.875 joules. And we'll get the same answer for both of these two if we plug in all of our numbers from the problem that we defined in the beginning, proving to us that this is indeed an elastic collision. A billiard ball traveling north at a speed of 3 meters per second collides with another identical billiard ball that is at rest. So think of when you hit a cue ball into another ball. The ball that was moving stops immediately after the collision, so the cue ball freezes. After the collision, what is the speed of the billiard ball that was initially at rest? So here's the cue ball. It's fired upward at this stationary ball. Well, the stationary ball now starts to move where the cue ball comes to rest. Okay, and this is an example in pool that you see a lot. The cue ball stops right after the collision. So let's take a look at what we've got going on here. Well, for this problem, we have momentum before and momentum after, but initially only the first cue ball is moving, and it's moving with a velocity of 3 meters per second. Well, the masses here are identical, so we could say that M1 is just M, and M2 is also just M. They're the same masses. And we want to find V2F. We also know that V1I stops after, V1F is 0 because it stops after the first one. And we know that V2I, the velocity of the second pool ball, is 0 initially. So this makes our equation easy. It becomes M1 V1I plus 0 equals 0 plus M2 V2F. These zeros are here because the first ball stops afterward, but the second ball wasn't moving initially. Now we remember that the m's are the same, so this becomes m v1i equals m v2f. Well, the m's cancel because they're the same, so v1i turns out to be just the exact same thing as v2f. Since v1i was given as 3 meters per second, that means that the final velocity of the second object will also be 3 meters per second. And this makes sense. This is a complete transfer of momentum from one pool ball to the other. Example 4 says, a pellet with a mass of m is fired with a velocity of 24 meters per second into a resting clay cart with 11 times the mass of the pellet. From this information, determine A, the velocity of the pellet-cart combination after the collision, and B, in terms of m, the amount of energy needed for the pellet to deform and fuse with the cart, or to really just embed itself in the cart is the word we're looking for. This is a really good example of a ballistic pendulum also. And a ballistic pendulum is the example where if you fire a bullet into a wooden block that's on a pendulum, and you can see how high up the wooden block moves, you can use conservation of energy to figure out, and momentum both, to figure out the velocity of the bullet when it was fired based on how far up the pendulum moves. And this is how muzzle velocity was calculated for a while. All right, now let's get back to the problem. It's the same idea now, but we don't have a pendulum, it's just a cart. Okay, and this cart is made of clay, and the bullet is going to embed itself into the cart, causing it to move forward. So let's list what we know. We know that beforehand, only the pellet is moving with a mass of m and a velocity of 24 meters per second. So the momentum beforehand is the mass of the pellet, m, times 24. And that equals the momentum of the system afterward, which is the sum of their masses, m plus 11m, times the final velocity of the system. And notice here that this 11m comes from the fact that the clay cart has a mass 11 times that of the pellet. So this will give us a 12m here. So we've got 24m equals 12mvf. Well, notice right away, m is on both sides of the equation. M can cancel. So we have 12vf equals 24. Divide by 12, we'll get vf equals 2. And what you might notice right away is that the mass of the pellet or the system went from being just m to 12 times that. And you'll notice that the velocity went from being 24 to 2, which is 1/12 of that number. The second part says to find the amount of energy needed for this to occur in terms of m. So in terms of m, let's see what that means. Well, the kinetic energy initially is the energy from the pellet, which is 1/2 the mass of the pellet times the velocity of the pellet squared. The kinetic energy at the end is going to be 1/2 times the mass of the system times the velocity of the system squared. So in the end, what we end up getting here for these two numbers is 288m and 24m, and these units are joules. Remember, m is mass of a pellet in this problem, not meter. M is the mass of any pellet. So if this pellet were bigger, it takes more energy initially, and there's more energy final. So if we look at the difference here, let's look at the delta KE. It's just going to be 24M minus 288M, which will give us a value of negative 264M joules. This means, if you look at this, that this is the amount of energy needed for the pellet to embed itself into the actual clay cart. So we can see as the mass of the pellet increases, the amount of energy needed for it to actually embed itself will also increase. Your homework for this section is from 4 different pages here.